part 4 of topic 8, starting off with solar radiation, in which you need to be aware of the sun radiating constant here, which is watts. 3.9 times 10 to the 26 joules per second. Energy and intensity. Energy spreads out in a sphere with a measured intensity of 1380 watts per meter squared. You've already seen that in previous slides. And it should be noted that the closer a planet is to the sun, the more intense that value becomes. So the brighter you will see. Here's some different graphs, pictures, charts that will show you about different solar constants. Interaction between light and matter, talking about photons when you have excited electrons. Light from the sun is made up of photons of many different wavelengths. This was already discussed in section 2 when we talked about photons and how the electrons are excited when they move down in energy levels. Therefore, light is emitted, and when they move up in energy levels, light is absorbed. Photons interacting with atoms can excite one of its electrons into a higher energy level. This only occurs if the energy of the photon is exactly the same as the energy needed to excite that electron. That's the only time you're going to see the electrons that are going to jump to a higher energy level due to interactions with photons. Then the photon disappears. If you see scattering of light, this means that the electron has moved to a lower energy level. Electron has now moved to a lower energy level. Ionization. We started to talk about this in topic 7. Ionization. If the photon is of a higher frequency, then it's also going to have a higher energy because your Planck's constant, obviously, will stay constant. So E equals HF would be used in this scenario. If the photon is of high energy, an absorbed photon can cause the electron to be ejected from an atom. The value of the energy of a photon does not have to be exact. It just has to be big enough to get the electron away from the atom. So it needs to be big enough to get the electron away from the atom. Excitation of molecules, not just atoms. Molecule is made up of several atoms that are held together by electromagnetic force. Different forms of energy that the atoms will then experience, they'll have internal energy, but they can also have some mechanical energy. And your different forms of mechanical energy would be kinetic energy and potential energy. Frequency of oscillations. If the frequency of oscillation is equal to that of a photon, resonance will occur. Resonance will occur, hitting that natural frequency, right? That's all the way back to like topic 4 that we talked about that. Frequencies tend to be lower values in the IR section of the EMS. Frequencies tend to be lower values in the IR section of the EMS. Now when we talk about absorption, solids can absorb many different wavelengths of light. When energy is absorbed by electrons passed to an atom, the temperature increases. Absorption increases temperature. This is why we wear black, right? Because black will attract the heat and then it stays, thus insulating us. Whereas more so in the summertime, you want to wear like light colored clothing because it more so will be reflected then, thus keeping the body temperature at a lower amount or the same amount, not increasing it. Okay, so when solid molecules are given energy, they can vibrate and give out low frequency radiation. The low frequency radiation that they give off would be emissions of IR. Albedo is going to be something that will be introduced to you now. Make sure that you do understand this, okay? Albedo is the ratio of reflected radiation to absorbed radiation. Snow has a very high albedo, like about 90%. Well, why is this? Because most of the light is reflected. Most light is absorbed, though, on the forest floor, so if we were comparing this to like the Amazon, then you would see that it would have a lower albedo. The average for Earth is 30%. When electromagnetic radiation is incident on a surface, that means the incoming angle is the incident angle, it is either absorbed or reflected. If it is absorbed, then that surface becomes hot. If it is reflected, that surface stays colder, hence why the snow doesn't melt immediately. There on the right-hand side, we have a slide that shows you the reflecting of light and the absorption of light thus talking about albedo. Blackbody radiation. You have a PhET simulation to complete on this. So after this section, I would suggest that you work on that simulation. If a solid is heated, it will emit a wide range of frequencies. Spectrum of light then from the solid would be a continuous spectrum, many colors, because it's made up of many wavelengths. Low pressure gas will only show several emission lines, so only several particular colors will be shining through. For black objects, they absorb all wavelengths. So if heated, that means that the emission of all wavelengths will be seen, but not all frequencies will have the same intensity at this rate. If you do have an increase in temperature, you should see a shorter wavelength though. Okay, an increase in temperature will give you a shorter wavelength, thus a higher frequency. Make sure you do this PhET simulation. Wavelength calculation. From this, you're going to use your wavelength max equals your B over your T, T meaning your temperature. Your B is your constant here, measured at millikelvins, okay? 2.89 times 10 to the negative third. Stephen-Boltzmann law. This relates power emitted per unit area to the temperature of the surface. So power per unit area is tau times kelvins to the fourth power, whereas tau is going to be a constant, TAU, and that is 5.67 times 10 to the negative 8th watts per meter squared kelvins to the negative fourth. As the temperature of a black body increases, intensity of radiation increases. That is seen by the graph on the left-hand side and also the graph on the right-hand side. You will be able to see this relationship here. As temperature increases, so does the intensity of light. Temperature of the Earth with no atmosphere. So what if we had no atmosphere? As the temperature of the Earth increases, it will radiate until the amount of energy radiated equals the amount of energy absorbed. Then Earth will stay at the constant temperature. Well, guys, stop and think. That takes you back to the second law of thermodynamics. If you're at the same temperature, then that's quote-unquote the end of the world. But we can calculate how hot the Earth should be by ignoring the atmosphere, which is intensity, and half of the Earth receives radiation. This is the calculation that you would choose to use. The average albedo of Earth is 30%, in which 70% is absorbed. Therefore, the absorbed energy per second is 1.23 times 10 to the 17th watts. Next, heat that's radiated by the Earth, we would use the Stephen-Boltzmann equation. So from this, you would get 2.9 times 10 to the 7th times your temperature to the fourth power. This equals heat absorbed, so T can now be calculated. So by calculating that, the average temperature on Earth is 255 Kelvin. 255 Kelvin. Well, I'm sorry, if there was no atmosphere, the average temperature on Earth would be 255 Kelvin. Well, that's negative 18 degrees Celsius, which is pretty darn cold, right? Well, why isn't this the actual temperature of Earth? Because Earth's atmosphere absorbs some of the radiation that's radiated by the Earth, which in turn is the greenhouse effect. So if we had no atmosphere, we'd be at 255 kelvins, but we're at 288 kelvins, which is the idea of us having an atmosphere. This is looking at emissivity. Defining this is the ratio of the energy radiated by a body, black body, to the energy radiated by the black body of the same temperature. The average temperature of Earth, 288 kelvins, which means that if Earth were a black body, it would be at 1.99 times 10 to the 17th watts. Well, it's not. We see back here that we are at 1.23 times 10 to the 17th watts. 1.23 times 10 to the 17th watts. So therefore, emissivity would be 1.23 divided by 1.99. So we have an emissivity of 0.6. Chart on the right shows you some others for some common metals. Absorption by the atmosphere. Radiation has to pass through the layers of the atmosphere before reaching Earth's surface. Well, the outer layers contain ozone that absorbs higher energy parts of the EMS, such as UV, X-ray, gamma. But IR, as you have noticed, has played a big part in this. So how's IR absorbed? It's not absorbed by the atmosphere, it's absorbed by water vapor and CO2. So what's in the air prior to reaching the layers of the atmosphere? Well, the ground also absorbs some of this. And this is depending on the albedo of the ground. Some radiation is reflected, right? Snow, for instance, versus the floor of the rainforest. Remaining radiation is absorbed by the ground, thus increasing the temperature, which is calculated from surface heat capacity. Surface heat capacity here on Earth, 4 times 10 to the 8th joules per kilometers squared. For the absorption spectroscopy would be measuring the intensity of light of a known wavelength as it passes into and out of a gas. Some of you have done this in chemistry before. You use gas spectrometers, gas specs, spec 20s, and figured out some different values based on different wavelengths of color, light, what was the alcohol that you injected into the machine. With the greenhouse effect, IR radiation that is radiated from the ground travels upward through the atmosphere and is not absorbed by the water vapor or carbon dioxide. Those molecules become excited, which raises the temperature of the atmosphere. IR is then radiated in all directions. By reducing the amount of radiation that's leaving, the temperature at which a balance of the amount of radiation arriving and leaving will be higher, so thus increase in Earth's temperature. So look at this simulation here on the greenhouse effect. Okay, check out that simulation, help you answer some questions. Now that we've talked about the greenhouse effect, what about global warming? Global warming, in essence, is the increase of Earth's temperature. How do we know this? Well, we look at ice cores. Samples of the ice cores show that each layer indicates 1 year's worth of data. So when you analyze the trapped gases that are in each of these layers of the ice cores, we're looking for heavier isotopes. The heavier isotopes will indicate colder years, i.e. colder temperatures. When the concentration of CO2 increases in each of these cores, you will see an increase in temperature. So what they can analyze is the amount of CO2 per layer. Low amounts of CO2 mean colder years, which means higher, heavier isotopes, whereas higher temperatures means higher concentration of CO2. Causes of global warming would be more sunspots would create more energy that would be emitted. Since Earth is an elliptical path, we would have enhanced greenhouse effects because sometimes we would be receiving more direct sunlight from the sun. Such greenhouse gases contributors would be water, carbon dioxide, methane, and nitrous oxide. That sums up your topic 8 notes.